Okay, so today we're going to explore this topic, instantaneous rate of change, by using the slope of a function to kind of get the idea of some of the big topics that we have in calculus. So there are three that we go into: limits, derivatives, and integrals. And we're not talking about integrals here. However, by talking about the slope right now, we are pretty much talking about a derivative. And sometimes we have to approximate what the slope is or understand getting like smaller and smaller, closer and closer values. And by looking at a table, it kind of gives us that idea. And that is one of the things we can do with limits, is to evaluate a limit numerically and taking a look at its graph. So that's why this is going to be explored. Okay, so when you're asked for an average rate of change, you're just doing slope. Okay, you should know slope is change of y over change of x. Okay, in the future, you may have slope be looking a little bit different. For example, you may not just have like a y value listed. Let's say you have to figure out its function value. So f of some number minus f of the other number. Okay, and typically there's, a measurement between the two values, okay, for y. And that depends on your x values. So one is going to be further away, okay, some change of x value from the other, okay? And if we take our x values here and we subtracted them, we would get change of x, which makes sense because, well, that's the change of our x values. So, this is in the future, okay? So if you're a little overwhelmed, don't worry, okay? Let's focus on knowing this. Now, another thing you need to know is that an instant is a point. So an instance, like a moment, it's a place, it's a location on a graph. So that's why it would just be a particular point. Sometimes we talk about an instant is x equals 2, or at the point x equals 2. Okay, so those words can be interchanged. And here we go. So below this is really supposed to be a table, but I kind of lost all the lines for tables, so I just kind of typed it out like this. So if you look, Miss Pelosi was driving for 6 miles, and she passed a location, and it was at 6:43 in the morning, and then at 24 miles, she was at a different location at 7:20 in the morning. I am obviously an early bird, but besides that, if let's say I wanted to find my average velocity, okay, usually miles per hour, so we need to know the distance traveled, that's the miles. So it's pretty easy. I'm going to do 24 minus 6, so that's 16. I'm sorry, 18. I got ahead of myself. I was still writing the 6. And then the change of time. So you can probably calculate, so that's 47 minutes. Okay, but if I do want to keep it in miles per hour, then I'm going to want to change that, or at least keep it in fraction form. So 47 over 60, okay, comes out to approximately 0.7833. Okay, and of course, if it's still part of our work and not a final answer, then we typically keep it to 4 decimal places. Okay, and so if I divide this in both cases, I get 22.980. Okay, you don't have to write the 0, but I did round to 3 decimal places to get this. So our answers must be to 3 decimal places when we are working in AP Calc. And if I had kept this fraction and put that in there instead, I actually get the same approximation. Okay, and this is your miles per hour. So we just figured out the average velocity or average rate of change. Okay, but now what about an instant velocity? Let's say at a particular point, what is my rate of change, an instantaneous rate of change? So I'm trying to underline here. I apologize for looking like I crossed that out. So if I'm looking at a particular instant, at that point I'm not measuring how many miles I did on my trip. You know, my odometer's not really giving me anything at that particular instant. So is that 0 miles? At a particular moment, time's not moving, I don't think. Okay, is that 0 hours? So if that's the case, and I figured out, hey, this is my distance traveled and the change in time, because it's not moving, I'm getting 0 over 0. By the way, that's called an indeterminate. Okay, we'll talk more about indeterminates. We cannot determine an answer. Okay, we cannot work with indeterminate, state them as an answer, do plus 5, can't do 0 over 0 plus 5, nothing. So how exactly we calculate it is through really small intervals near the actual values that we're looking at. Okay, so let me explore something else with you. Okay, so one of the things that I'm going to go over with you is graphing piecewise functions, common functions, stuff like that. So we're getting an idea of like how to sketch our curves. We need reference points. I'm in the habit of always writing which is my x and y axes because I often end up teaching problems that are in 3 dimensions, and it kind of looks different when we have to work with a z-axis. So it was always taught to me to write which is my x-axis and my y-axis, reference points. So you don't necessarily have to write out every single point. Okay, like this is fine. Okay, it looks like I'm just kind of going to sketch here, y equals x. Alright, and this is a good one to kind of discuss what's going on here because we can see the slope of the line is 1, and due to that fact, if we were talking about the average velocity or average rate of change, hey, we could see the slope, it's 1. If we had a table, it looked like this, and we can calculate that, but hopefully, if we're looking at another point, okay, let's say when x is 3. Okay, so at that instant, we want to know what's going on there. Okay, we would probably figure out, well, we know its y value, but we would probably figure out, well, what's going on by using 2 and 4. But the idea behind this is to get really, really close values because this is not always going to be a straight line where we can identify the slope, but rather sometimes when we're looking at data, it's going to be along a curve. So, okay, I'm just trying to sketch out something really quick, hopefully. Here's a curve. So I want to know, like, what's going on, not between, like, 1 and 10, but, like, what's happening at this particular moment. So at this particular moment, okay, I don't have really a line to connect that'll give me a good idea, because if I connect from here to here, which seems to be where I'm plotting when x is 1 and x is 10, it's so far off of the actual function, and I need a slope. Okay, I don't have a slope at a particular point, just one point I have between two. So what happens is that we try to take values that are closer and closer and closer to when x is 3, if that's the one that we're looking at. So if, let's say, I was using 2 and 4 again, that gives me a better idea of the slope. But now if, let's say, I use 2.5 or 2.99 and 3.01, I'm getting closer and closer values, and hopefully you can be able to see that I'm looking at the slope of a tangent line along a curve. So if you can figure out the slope of the tangent line, then you can figure out your instantaneous rate of change. And the idea of looking at closer and closer values at a particular point is important to limits, and the slope of the tangent line at a point has to do with derivatives. And I've got to talk about curves and lines with you, so we'll get to common functions, and let me know if you need any help with those and graphing piecewise functions. And if you have any questions, well, what is a tangent line? Why did you use the word tangent? Let me know. We have so much to explore and go over, so it should be good. Again, if you need to find or approximate the instantaneous rate of change, then you're looking at basically finding the average rates of change over small intervals, okay, that are really, really close to the value we're trying to find. So good luck, and yeah, let me know if you do have those questions. Bye.